Today I would like to talk about the future that I see through this strange amoeba-like organism. So the center of gravity of my talk is located at the future, not the summary of past results. So I hope you could just relax and enjoy my talk. So I have been playing with this amoeba-like organism, which is called, the name is true slime of Physarum polycephalum. So this is a scale bar, and you see this is a quite large, huge organism, but it is a single cell. It's a single cell, but has many cell nucleus. So if you cut a piece at the tip, this piece can survive as an individual. And if you contact more than one individuals, they fuse into one single cell. So meaning that this system is quite homogeneous. So it is known as one of the model organism of decentralized information processing system. And what is interesting is that, so this is the schematic of the structure, single cell. And at this outer layer, which is composed of actin and myosin, which is components of our muscles. And they exhibit interesting oscillatory behavior. So at the period of about 1 to 2 minutes, it relaxes and contracts periodically. So this is a movie. This is a real-time movie. So we are watching the Y-shaped structure. And now this part is contracting, and this part is relaxing. So the intracellular fluid flows from the bottom to the top. But you see the reversal of the flow, meaning that this part starts to shrink. And you see here also the direction is reversed, like this. So it's very interesting to see this organism by using microscope. And at every 1 minute, you can see the reversal of this flow. And repeating this flow, this organism changes its shape and even moves around. This is a very sophisticated study that was done by Professor Takamatsu at Waseda University. She created a kind of living coupled oscillator system using one single cell. So this is a plastic barrier which cannot be overcome by the organism. And you see this red and blue pixel represent that the thickness increased or decreased. So you can see these two oscillators are synchronizing in antiphase. And she said that this width of the channel corresponds to the coupling strength, and the length of the channel corresponds to the time delay between the two oscillators. And if you increase the number of the oscillators, you can see more complex patterns. In this case, these two oscillators are synchronizing in phase, whereas this one performs the antiphase synchronization. In this case, you can see 120 degree phase difference are there, so you can see the rotation. And in this case, while these two oscillators perform one cycle of oscillation, this guy performs 2 cycles of oscillation. So the point is that this organism cannot keeps its volume constant. So these 3 modes can stable while maintenance of the volume conservation law. And interestingly, we can observe spontaneous switching among these modes. So after repeating, for example, 5 or 6 cycles, you can see stochastic switching among these several modes. And this is another important study done by Professor Nakagaki from Hokkaido University. He showed that this organism has some smart function. So this black barrier is shaped like a maze, and this yellow part is just a single cell. And when he put 2 food sources, this organism changes its shape and connect the shortest route between the food sources. And so you may recognize, so this organism has oscillatory dynamics and interaction with long and short range, meaning that in one single oscillator, this is a short range interaction between actin and myosin. And also we can have the long range interaction between macro scale oscillators. And also we can see synchronization and the fluctuation, stochastic behavior. And somewhat this one is something like compared to the learning, because it's kind of reinforced learning. You know, the Hebbian rule. In between these two regions, we have the frequent flow of the intracellular zone, and it reinforces the connection. So it's something like learning. So I see the properties of brain are installed even in the single cell. That's why I'm interested in this organism. And then we created a kind of neural network computer using this single cell. So this is a barrier and this is an agar plate. And when we cut the piece and put it here, then this guy can survive as an individual. And we consider that each of these, in this case, there are 16 lanes, and each of the lanes are considered as a neuron. And we assign the state, real number state. If the lane is fully occupied by the amoeba's branch, we assign just state 1. And it's empty 0. So when it's occupied half, then 0.5. And this organism doesn't like light. So when we illuminate this lane locally, after repeating several cycles, this organism withdraws its branch. And when we turn the light off, it elongates again. So we monitor the shape of the amoeba using the camera and send this image to this PC and determine some image to be projected by those kind of projector. And so as this organism changes its shape, we change the illumination pattern. So there is a kind of feedback. And by assigning some certain appropriate rule, we can lead this organism to solve a problem. So this is a typical example of the problem solving using the single cells. For visibility, let's see in this binary color. So red and blue pixels again represent the thickness increased or decreased. So you can see the phase wave traveling through the body. So this is a kind of complex spatio-temporal oscillatory dynamics. And basically this organism wants to maximize its body area so that it can maximize the absorption of nutrient from the agar plate. So there are 16 lanes, and this organism wants to elongate all of these 64 branches, basically. But we apply some feedback. So we measure the length of each of the branch, and when this length exceeds certain threshold, we illuminate some other branches according to certain rule. Then this organism wants to maximize its body area, but should minimize the risk of being illuminated. And through this kind of trial and error process, this organism finds the combination of the branches, which can elongate it under non-illuminated rain without being illumination, by minimizing the risk of being illuminated. So in this case, you can see that 1, 2, 3, 4, 5, 6, 7, 8 branches finally elongate. And this is corresponding to one of the feasible solution of the traveling salesman problem in this case. This problem is a very famous combinatorial optimization problem. And the traveler, the salesman should travel around all of these cities and should come back to the starting city, but should minimize the travel expense. So he or she should minimize the route length. So in this case, you see C1 means that city C was visited first, then H2, the city H was visited second, D3 third. So these 8 branches represent in an abstract space this route colored red. And the route length of this route was the 128, which was not actually the shortest route. In this case, shortest route was length 100. But the solution found by the amoeba was pretty good, because the worst case was 200, and the mean value was 150. And so we think that this computation can be done by hybrid between the control dynamics and the amoeba. And we call this control bounce back control, and its control principle is quite simple. When the light is on, branch should shrink, and light is off, branch should expand. But as long as this amoeba follows this control principle, it just simply goes down this energy potential. So it's going to be trapped at local minimum. But you see this organism has oscillatory dynamics, and sometimes even in the presence of light, the branch expands, and even in the absence of light, it shrinks. So thanks to this fluctuation, this stochastic behavior, it can find a better solution. And it turns out that this fluctuation is not random. Because you see, these branches are the single cell, and you saw the synchronization. So these branches are spatially and temporally correlated. And so what we were interested was what is the contributions of this reservoir-like part at the center disk to computing. And then we performed this experiment. So this is the case where we start from one single cell, and when we illuminate all of these 64 branches and wait for this organism to shape like a disk, and just start. So that's what we saw in the previous movie. And another case is this is a control experiment. We insert kind of separation wall and put these two individuals. So they never contact. And then perform the same feedback. So what's going to happen? Another case, we use just single individual, but before the computation, we insert this separation wall and wait for certain minute to see if this correlation can be memorized or not. Okay, these are the results. So in the normal case, experiment A, the success rate, that this is a percentage that the amoeba could found one of the feasible solution, was almost here. But in the case of B, the control experiment, when we use two different individuals, this success rate degrades significantly. And what is very interesting is that by changing the time that we start computation after inserting the separation wall, so this performance degrades kind of linearly. So it means that spatial temporal correlation is necessary for solution searching dynamics in an individual reservoir. And also even separated two reservoirs maintain the correlation over a long time, like 90 minutes. This is another experiment that we performed a time series analysis of the spatial temporal dynamics exhibiting in this reservoir part. We counted the number of the traveling waves. So in this case, the body was separated into, in this case, 3. So we counted the number of these separating borders. And this is the number of the separating border, and this is the root length that was found by the amoeba. So shorter is better. And in this case, with smaller numbers, it means the dynamics is coherent. So it clearly indicates that shorter length, higher quality solution can be found by the dynamics of the reservoir with stronger spatial correlation, stronger coherence. So these were what we found through the biological experiments. So we played with this wetware. But after that, we extracted a kind of software. So this is algorithm extracted from this spatial temporal dynamics. And we tackled another solution, another problem. The problem other than the traveling salesman problem. The problem is called satisfiability problem. This is also a combinatory optimization problem. And it turned out that this algorithm gives us very good performance. So encouraged by these results, we are now trying to create kind of nano-architectonic devices to implement this amoeba-inspired model. So I'm going to explain these results later. And also, we are trying to tackle some practical applications that this amoeba-inspired model or devices can apply. And today I would like to talk about, if the time allows, I'm going to talk about this. This model can be used to simulate chemical reactions. Okay, let me explain about the problem, satisfiability problem, abbreviated as SAT. So this is a kind of constraint satisfaction problem. So one should find an assignment of the variables, logical variables, which can make the whole formula true. So in this case, we have 4 variables, and each of which takes true or false, 0 or 1. And so let's see what happens if we input 0, 0, 0, 0. So in this case, these constraints can be satisfied, but these cannot, this one cannot. So this 0, 0, 0, 0 is not a solution. In another case, 0, 0, 0, 1, these 2 conditions are not met. So this is not a solution. And in this instance, just 1, 1, 1, 1 satisfied all of these constraints. So this is the solution. And so this was very, in this 4 variable case, we only had 16 solution candidates, so it's very easy, but the number of possible assignments grows exponentially, so the combinatorial explosion occurs. And this problem is known as NP-complete. So many NP problems, well, most of the case they have exponential time to solve, can be reduced to SAT. So when we have a fast SAT solver, it is believed that it can have many applications like artificial intelligence, bioinformatics, and information securities. So how this amoeba algorithm solve this problem? So this is, you can suppose that this is abstract software or hardware. And each of the branch of the amoeba is represented by just 3 states in this case. So +1, 0, and -1. And this is the analogy of the inhibition light. So if you illuminate the light, these branches withdraws with 2 steps. And the important factor is the fluctuation, I mean stochastic behavior. So the error here, the stochastic error occurs when there's no, even though there's no illumination, sometimes with a small probability this branch does not elongate. That's the definition of error in this model. And how to translate these logical constraints into this system? So let's suppose you see this is this branch represents that variable x1 takes state 0. And in this case, x3 should not be 0 because 0 or 0 goes to 0. And in this case, x2 should not be 1. So that's why at the next time step, we inhibit x3 0 and x2 1. And this one is also bounce back because these 2 are logically inconsistent. Let's see another case. In this case, 2 branches elongated. So x2 goes to 1 and x3 goes to 0, so x4 should not be 1, and blah, blah, blah. So at the next time step, we illuminate these branches according to these rules. So once you have this kind of logical constraints, we can generate these bounce back rules automatically. And by referring to these rules, we perform the trial and error process with the stochastic behavior. So the branches are shrinking and elongating and trying to find a stable configuration. Stable configuration means that in the presence of light, the branches withdraw. And in the absence of light, it's elongated. That's the definition of the stable. And then after certain time steps, this system goes to stable configuration. Then this is corresponded to the solution of the SAT. So this is a spatial temporal dynamics, and we have a trial and error process, and after that we go to stable. After certain steps, we go to the stable configuration, which is the solution. And we compare the performance of this amoeba SAT algorithm with the champion algorithm of the world's SAT competition. The name is ProbSAT. And so this is the reality. So now we are comparing the software which are run on the same computer. So the horizontal axis is the problem size, and this is the time after you press the return button, and then you get a solution. Just so the unit is second. So amoeba algorithm is significantly slower than this champion algorithm. But interestingly, if we focus on the number of iterations, amoeba is significantly faster. And the same goes for other ways to create problem instances. In terms of time, it's slower, but in terms of iteration, it's very fast. That's because this amoeba algorithm is not suited to run on this conventional computer, which is operating in a serial mode. So when we create some physical implementation of amoeba algorithm, which can reduce the time required for each of the iterations, we can expect that we can have the super fast solvers. So that's why we are now trying to move into the physical implementation. So this is one example which was proposed in 2013. And at this time, at this moment, we were interested in quantum dots. But I'm not going to the detail. Then we moved to the electric circuit. This was, at this moment, we tackle from very simple problem instance. And this is another numerical simulation which suppose that we can use a stochastic element, which is called electrical Brownian ratchet, which utilize thermal fluctuation to have stochastic operation. Then we numerically simulated that this system can solve the SAT problems. Then today I want to introduce the recent result, which is just not a numerical simulation, but experimental realization. But this is in a very primitive stage. We are just doing the breadboard circuit and confirm that we can solve 20 variable, very small instance. But this system supposes that we have the kind of amoeba-like branches with a capacitance, and we can also introduce the bounce back signal and this kind of random disturbance. And what is important here is that each of the variable has analog value. And another important point is that the time scale of this oscillation of the analog value variable is much, much faster than the times evolution of the digital feedback control. So this means that this analog dynamics we can use is much faster than digital clocks. And also this dynamics was found to move to the oscillation or solution. So meaning that this model exploits the analog physical dynamics that the electric circuit goes to convergent state for solution search. Yes, and some of you are familiar with the current state of the special purpose machines proposed in this decade or 5 years. So this D-Wave system, a Canadian company, have produced this first quantum annealing computer, which is a product. And this quantum annealing, the concept was proposed by Professor Nishimori at Tokyo Tech. This is another one, NTT, National Institute of Informatics, University of Tokyo, Osaka University, and Stanford University proposed a coherent Ising machine to solve the combinatory optimization problem. Another one, Hitachi is now doing CMOS annealing. And also Fujitsu and University of Toronto are doing digital stochastic search. So interestingly, most of, all of these concepts are from Japanese scientists. And then what we are expecting have this amoeba-inspired architecture will be compared to some of these concepts. But important difference between these these approaches and ours is that the variable, so they are dealing with the binary bit or spin, so this digital variable. And some of them are using physics, but some of them are emulating the physics. But our case, we are doing the analog variable, and also we exploit explicitly the physical dynamics and also the fluctuations. So from now on, we are going to tackle these questions. These are fundamental questions, I guess. And how does time required for reaching a solution grow as a function of a problem size n? What are fundamental advantages of analog over digital? How can we exploit computational power of nature, physics? So these questions will be addressed experimentally from now on. Okay, let's move to the application. So the concept of this chemical reaction comes from the observation of this spatial temporal plot. If we have this problem instance, this instance gives us 3 different solutions. So 1, 1, 1, 1 can meet all of these constraints, and also 1, 1, 1, 0, and 0, 1, 1, 0 can satisfy all of these constraints. So when we run the algorithm through time, we can observe that after this model finds this yellow solution, thanks to the fluctuation, this moves to other one, the green one, then blue one. So meaning that we can have some transition among these different solutions. And we can observe frequently the transition between yellow and green, but less frequently between yellow and blue. Why? Because this solution has just one single bit difference. But in this case, there are 2-bit difference. So maybe this can be corresponded to some kinetics of the chemical reaction. That's one point. Another point is that depending on the solution, the duration, the time that each of the solution can last are different. So maybe this duration can represent something like thermodynamic stability. This is the beginning of our concept for to extend amoeba algorithm to chemical reaction simulator. So in this satisfiability problem case, we have on one hand logical constraints are represented by bounce back rules and fluctuating dynamics, then we get a stable solution. So we thought that if we can represent some physical chemical laws in the language of bounce back rules, we can have some stable state as the formation of stable molecule. So this can be said as this is a goal. So large scale and long-term simulation of a chemical reaction may be possible with low computational cost by novel board approximation. So we are just now in the beginning of this project, and let's see a very simple case. We have now 2 nitrogens and 6 hydrogen atoms, and so each of the box represents the number of bonding between the atoms. So for example, this case, this nitrogen 1 and have triple bonding between nitrogen 2. So this box is colored, meaning that the branch corresponding to this box is elongating. And you see this nitrogen 1 and hydrogen 3 has single bonding, so this one is colored. So in this case, we have 4 bonding in total, but it's beyond the capacity of nitrogen. So we bounce back this bonded state with some stochastic inhibition signal. And in this case, this hydrogen number 4 has no bonding with any atoms. So we encourage this guy to bond with some others. So this is a basic philosophy. And in this case, this guy is just satisfied, so we lead this guy to stabilize its bonding state. So in this manner, we can represent these physical-chemical laws by stochastic bounce-back rules. And in this system, this state is one of the solutions. So represented by this kind of configuration. And 2 ammonia system is also a solution. And this one are the solution. So in this case, we have 4 different solutions. And this is the example of the time evolution. So starting from, for example, nitrogen case, after maintain this configuration for a while, then it moves to this case and another solution. So by accumulating the duration of each of these 4 solutions, we can evaluate a kind of thermodynamic stability. And we can also measure how frequently the transition occurs among these solutions. So the reaction rate or kinetics can be tuned by the probabilities of bounce-back rule applications. And this is one way to tune these parameters. You know, triple bonding among nitrogens are very strong, whereas single bonding is very weak. So we can tune the parameters, the probability, so that large bonding energy gives a small probability of the dissociation. So in this manner, we can tune the reaction kinetics somehow. And also, it's very important to introduce the polarization and or ionization. So these, by using the diagonal variables, we can represent the polarized state of carbon dioxide in this case. So carbon number 1 is positively polarized, whereas oxygen is negatively polarized. And we can induce this polarization occurs, and the oscillation occurs between these states. This is another case. We can have intramolecular polarization, and by introducing the rule, we can induce 2 carbons negatively positively polarized atoms attraction. Then increase the possibility to have the kind of condensation reaction. So actually, we are now starting to tune the parameters for this nucleophilic addition aldol reaction. And this is the stability of molecules with newly formed C3 bond. Okay, so this is just the beginning, and these are our future goals. So we want to have a large-scale and long-term simulation of chemical reaction with low computational cost, and which cannot be achieved solely by conventional methods like first principle calculation or molecular dynamics. So by combining these, all of these approaches, we are very happy if we could have this long and large simulation with low computational cost. And once it is successful, we can have a semi-quantitative prediction of unknown reaction path, unknown reaction kinetics, and unknown byproducts. And it's going to be very useful for drug discovery and new material exploration. Okay, so this is our future perspective. Spread in the 2-dimensional space. This is science, engineering, and software, hardware. So first we can tackle post-silicon computing using novel hardware and for practical purpose, like resistive memories, nanoelectronic devices, and quantum dots. And also, we can develop the software to achieve like protein structure prediction, and also robot control and automated drive. So these approaches will be very useful in the practical applications. And like I explained, the chemistry simulation can be supported with constraint satisfaction dynamics of this model. And when this is successful, we can contribute to the origin of life study that is happening in Earth Life Science Institute in Tokyo Tech, which is another WPI institute. Okay, this is the last slide. I would like to thank these collaborators, which is mapped onto this 2-dimensional space. Thank you very much for your attention.
Thank you very much.